Okay, so thank you everybody coming in person and those online. So we are very pleased to welcome William to give us a very exciting seminar on learning to impute and align with knowledge. I will share something that is not in the announcement. William, I have known William from 2013. That's almost more than 10 years ago, right? So we have been colleagues for 3 years. So he's visiting us for 3 months. Started mid-January, so William will be with us until mid-April. He spent 3 months of his sabbatical over here in Sheffield. I will not steal more time from William, so let's welcome William to give us his seminar.
Thanks for the kind introductions. So is my voice okay? Okay, so first
online, yeah, take it early.
Yeah, thanks for those who are in this room and also those who are online. Thanks for coming to my talk. And I have some title, right? I'm with the Department of Computer Science. I come from Hong Kong Baptist University. I've been there for 20-something years, so you can guess my age. And also, I'm also the Associate Vice President of undergraduate programs. You know why afterwards, okay? And first of all, I would like to really thank the Department of Computer Science, University of Sheffield, to allow me to spend my 3 months here for my sabbatical, and especially Professor Liu, okay, support my stay here so that I have a really nice environment, some quiet time to do some serious research. Thanks so much. And before I start, I think I have to say something really important. So there's going to be a first multi-modal AI community forum to be held on 25th of March, right? And then, of course, organized by Center for Machine Intelligence on the University of Sheffield. So you can just register right now, okay? So, and then I think it's going to be a very exciting forum for colleagues to exchange ideas. Professor, do you want to say something about this one?
No, yeah, okay, carry on. Yeah.
Just register, okay? Then we'll see. So back to a bit more about my background. So that's my commitment. So I have been working on AI and healthcare for the past around 7 to 8 years. Before I work on social network and others. And other research work, you know, because of my associate vice president's commitment. Okay, someone said that's a big term. Okay, but anyway, so I spent some time, quite some time actually, overseeing some transdisciplinary undergraduate program. You know, interacting arts and technology, interacting health and also technologies. That's my expertise. Okay. And also we have a very exciting program which is called individualized sub-majors, that is students can design their own majors. In case you get, I mean, you're in charge of this, okay, and I can learn something from you, please let me know, okay, and so that I can have more discussions with you on that. Okay? And also I also do some other miscellaneous things. I'm also developing an AI literacy course for the whole university that involves colleagues from different faculties. Okay. Also quite interesting and also challenging for me. I understand that Professor Liu is working on a multidisciplinary AI papers, so I hope that I can help. And also I get involved in some metaverse development things. That's why my time schedule here is 6 a.m. I have morning meetings with colleagues in Hong Kong, you know, working on some of this project. So afternoons, I can have more quiet time to do my own research. So that's my life in Sheffield. Try not to overrun, so I speed up a little bit. Okay. So for AI, so there are so many different methods that we can work on, right? I spend a bit more time together with my students, okay, on say tensor factorization, decompositions, more on irregular one. Okay, I'll let you know why afterwards. And of course, deep learning, okay, representation learning, so which is very hot in these days. So I also spend some time together with the students on that. I have a Bayesian, you know, inference background, aside from my PhD. So that's why I also work on the, you know, deep generative models of it. Okay, but the lower three are the healthcare applications. And actually, I got each of these. I got funding first on computational phenotyping. And then I move on to do a bit more on predictions. And then recently I also got projects on radiology report generations. So you see these two arrows, right? Actually, very often, so I start from the problems. And then there are some existing methods used for those problems. And then I find that some assumptions which are wrong, okay? Either by my own, understanding, or I talk to these three victims, okay? This one is health implementations of health authorities in Hong Kong, okay? And that's why I understand a bit on that from him. And second one is Keith. Keith is a radiologist. I work on radiologists report generations. I cannot do that without the help of radiologists. And the last one is Terence. Terence is the associate consultant of an ICU, intensive care units in Hong Kong, Tuen Mun Hospital, in case you know a bit about Hong Kong. And I keep asking them some questions following that. Okay, based on my those deeper understanding on the problem. Sometimes we got ideas of extending on these methods, and some more powerful methods actually can help this. Okay. This is my cycle of doing research for the past 5 to 6 years, and it's I really want to thank them for helping me. So since I know that there's diverse backgrounds, okay, among the audience, so let me start from something very basic. Suppose patients come in to see medical doctors, okay, in an encounter. And then so probably through some examinations, there's some diagnosis, put in the records, right? And then some further records are required, right? So then the request is put in the records. And the medication as well, also in the records. That's why in the EHR records, we have this more structured data in the database, right? We can just retrieve that. And if you are not so lucky, got some problem with say bone and whatever it might be. Actually, I got some lower back pain for quite many years. So that's why actually before I come, I take a lot of X-ray and see receive related treatments. Okay? So that's why in the electronic health record, we also have a lot of radiological images. And also medical doctors also sometimes give reports, right? Text. And quite some important information stuff from text. I talked to the clinicians in Hong Kong, and then I say I studied lots of these HR data from the structured database. Okay, and then he said that you have to look at the clinical notes. Many details are actually put in the clinical notes, but not yet recorded in the database. Okay, so that why I think it's crucial. It's text, free text, and vital sign, of course, right? If you are actually admitted in the ICU, then probably you have this continuous monitoring of the vital sign. Then that's a time series. That's why we have this. And so, yes, lots of data. I like this picture a lot because this gives us perspective. The data are not recorded just for recording, not just for providing operations. It actually tells a patient journey. Right? So give a very simple example. I mentioned that we work on the radiology's image generations, right? Look at the X-rays and try and generate the report. And then the clinician, I talk to clinician, I say we need some very exciting things. And then he looked at it and said yes. But he also mentioned that when he looked at the X-ray image, he actually has the understandings of patient history, which is actually stored in the health records. Okay? Together with that, he tried to make some diagnosis. Okay, which means that when we do analyzing X-ray image, so if we eventually really want to have the clinical doctors, half of the data stored in the electronic health records should also be considered as well. Okay, I will briefly mention that in some of our works afterwards. And the journey actually takes time, right? So how to read this journey? So first I read it to the hospital on the left-hand side. There are some demographics, medical history, risk factors, all this record at the very beginning, right? Get in hospital after 1 day, so important that you have to be admitted to the ICU. So once you're admitted to ICU, you start to have this vital sign being recorded, right? Without the stay in the ICU. And then you have probably you during that period of time to time, you have some ECG reports. If you take X-ray, you have a R, right? Send for the radiology reports, and you take some medications, different lab tests. throughout stay in the ICU or hospital. They appear recorded at different time, right? They're recorded because the clinician would like to know the health conditions and how it changed over time. So this perspective is, I think, it's very important, okay, to drive our research afterwards. Okay. I'll probably get back to this afterwards. And very important, okay? So health data, in fact, is multimodal. Okay, that's why multi-modal related methods are important. But also, I'll make a statement afterwards. We're not just because they're multimodal, so that's why we apply some multimodal methods. What we also probably need to understand why they are produced in different modalities. There must be some reasons, right? Anyway, I'll move back to that point. So when we do predictions, normally the experiment setting is like this. So that's the patient journey. Okay, so we hope that these are data that we have. We try to take our observation windows, probably the first 2 days, 3 days. Okay, and then for the journey, the last part, okay, eventually the patient discharged, their discharge report. Based on that, then we hope we can know for this patient journey, what's the outcome? Okay, so it can be successfully discharged, which is okay. If not, then probably somehow some patient eventually will die in the ICU. Okay, then there will be a label marked in the record. So in hospital that. With that, then we can do prediction tasks. Normally people call mortality predictions. Okay, because with the labels, and then we have the observation windows, then we can do predictions. Okay. So mind you that if you make the window really long, very close to the discharge, all methods will be very good, right? Because you basically know the final state of patients, all methods will be good. Okay, but if you know everything, then what else we can do? So normally people make the observation window not that long, so that we can do earlier, understanding of patients, so that predictions make sense, and that predictions probably can do something about this. So far, we're only working on the prediction. We haven't worked on the treatment effect in the treatment plan. We haven't worked on that. We start a little bit, but we need some time to pick up more of the backgrounds. Okay, so that's how normally we set the experiments afterwards. And other mortality predictions, people also do disease progressions. That is, given this observation window after some day, so what could that be some abnormalities that will happen? If you can predict this, maybe you can do something about it. Okay, so that's the background, how to set up the predictions experiments. And we also spent some time to understand the medical ontology. Let me explain to you what we think are, in case you don't have background. So I think most of us understand, right? Trying to organize different concepts and their relationship. Okay, just like one concept, I am a professor, and there's another concept called Hong Kong Baptist University. Okay, and then I'm a professor. It's a relationship. I'm a professor of that university. Now, two concepts, one relations, right? And if we extend this concept to lots of different domains, we can create many different ontology. And for healthcare, explain the consumption. I can see this. Okay. Okay, yeah, so again. Missing data problem. Yeah, I mentioned about the missing data problem. I have the screen just that not all of you can see it.
You can continue. I think
just
online.
But also, right. So on the left-hand side, you see there's an ontology, but it's very popular in ICD. Okay. Right now we have ICD 9, 10, 11. Basically, different medical concepts are categorized in a hierarchical manner, right? So one category is injury and poisoning, and under injury and poisoning, there are several subcategories. Say poisoning, fractures of skull, mislocation, so on and so forth. Okay, organized in knowledge this way. And this part is what's called SNOMED. For those who are in the medical health informatics field, they know these two ontologies pretty well because they're famous and important. This one on the right-hand side, SNOMED, they have not just the hierarchical relationship, they also have some other relationship which are very useful actually. For example, they have fine sign. So asthma happening in the lung. Lung actually near to the heart. And there's some disease actually related to the heart. Through this ontologies, then you probably can link up to, so these two diseases could be related by, not just by they happen together in the electronic health records, also by these ontologies. Okay? Why I mentioned this? When the clinician look at these data, the electronic health records, patient journey, they also have some knowledge in mind, right? And so I think it's important, and we later on we find that it's actually quite helpful to incorporate this knowledge in. Okay? So I hope that I provide you some background so that it's easier for you to understand what we're doing. This slide don't have to explain. All these resources, okay, what we have been playing around with for the past some years. Electronic health records, data, XRay, and also methodologies. Okay, so if you're interested, you have been working on it. Okay, so you can take a look on this. It's pretty rich. So after working on several papers and work, so two key fundamental issues. One is missingness. Right? We encountered some missingness situations. So again, I like this picture. Okay. So probably you see that okay, at certain time interval, you have some modalities, but you don't have some others. Right? So you have lab test result here, then some report, and in between, and you don't have any focus node. But you have some lab test result, and you have some vital sign. Okay, so you can see the missing modality is quite common through our whole patient journey, right? And other than this, you also have some missing features because of like hardware issues. Like somehow I read some papers, right? Maybe the patient is not asked about diabetes, okay? And so because of that, that's not recorded. It doesn't mean that I don't have diabetes. Just no one asked me. Okay. There are all kinds of different reasons that we may have missing features, missing modalities, which is hard to know. If people know, then they fix it. Right? It's hard to know. That's the first thing. The second thing is that when we apply, say, deep learning things, try to learn the features are for prediction. The features are not used for organizing the knowledge. We human beings organize knowledge in our brain based on our knowledge, right? Just like the ontologies that I should mention to you. If they do not align with each other, maybe for some prediction tasks it's okay. But we find that we demonstrate that if we can properly incorporate this, we can have higher performance on some parts. Okay? And today I only focus on for this part, second problem. I've only focused on radiology image generations. But we also apply it to some prediction tasks, also get some improvement, which I can talk about this afterwards, okay, if you are interested. So I start from here for this extracting hidden interactions among the clinical events. That was my previous sabbatical. I start working on this problem. And then based on that, I move on to find that missingness and then align with knowledge to be two very important issues. So I have more paper published on this two directions. And basically we talk about this one, and this one in the following course. And one is on the binary data imputations. And now one is going to be presented a few days afterwards because in the Shef.AI conference that we have in Vancouver. I won't be there, my student will be there to present the paper. And the last one we published last year on the radiology report generations. And so that's in TKD. So imputing missing data. If you are in the field, there are many methods already. Okay. And so, researchers need to find something we can continue to contribute. There are many. Okay, I read some. This one is from us. And there's a competition actually on this. If you're interested, you can also make reference to that. Some years ago. Okay. But not much work on binary. And because of binary, if you got 0, or 1, 0 or 1, right? If 0, 0 is 0, right? So you don't know whether it's really 0 or I don't have diabetes. It's just 0. Okay? So that make the problem, at least not that many people working on this. Okay, to solve on this. Okay, and I hope that that makes sense also for those of you from the industry. Okay, that could be some problems on that. So problem statements. Okay, suppose again a patient in ICU state, day 1, day 2, all the way to day N, and there are different clinical features recorded. Diagnosis, medications, okay, lab card, so on and so forth. And here I just consider binary. Okay, for those of you familiar with the EHR data, for medications, okay, I prescribe a drug. You probably know that it should come with dosage. Yes, okay, but we didn't consider dosage for our work. And considering our dosage probably can be done afterwards. Okay, we didn't consider that. So only 1 or 0. Okay, so suppose I got a particular disease diagnosed, 1 in the records, and then some just are being prescribed, 1 in the records. Okay, but the others just missing or absent. I guess most of them are not. Most of the cases that this 0 really means 0. Okay, I think clinician will not play games, right? They try to do the best, but somehow for some reasons it's not recorded. Okay, so how can we identify them out? If this kind of missing is just flipping a coin, and same coin for all the 0, the count is also quite easy. Okay. However, if I say actually there are some observation bias, some diagnosis or medications is not recorded, there must be some reasons, but that reason is quite hard to know. Again, if you know, you will fix it, right? So which means that, okay, I'll explain it this way. So each of the 0, you have individual points. Okay, the missingness of each individual 0 may not be the same, can be affected by different factors. So we call it observation bias. Okay. And the observation bias is quite, it's not easy to understand the mechanism behind. So I hope that, and if we have this, then the prediction will be biased for sure. And so what we, to attack this problem, we try to model the observation, try to model the observation bias this way. Okay. Instead of taking this clinical sequence of clinical features and do the predictions with a lot of 0, some are really 0, some are we don't know. Okay. Instead of doing this, for each of the X, we estimate a Z, which is complete data disk. You really have diabetes, okay? But which is latent, we don't know. We don't know. Okay. So we assume that we have this Z, the complete data, and of course we try to infer that. Okay. And with that, we also try to infer the propensity score, which is basically the probability that if I really got diabetes, would that be recorded? Okay. If the ground truth happens, would that be observed? Okay. Again, this con is not. This can be very different for different records. Okay, that's a challenge. Anyway, so that's the model. Here we can infer this with latent complete data, okay. And then we can estimate this probability is accurate enough. Then we can use this to explain the data, and in this way we can learn the model. That's the rough ideas. It's not too hard to get this simple formula. Okay, that is try to get the posterior probabilities of I really got the diabetes. Okay, and these are just follow some base rule. We can continue to use the base rule. Again, the question is, if I can get this propensity score accurate, problem solved, but we don't know complicated. So that is the model architectures that we use to do these estimations. Okay, from this, so X basically the clinical features. If we proceed, then accumulate it and then have the history. Okay, if you predict that it's correct, it's just simple base. Okay, you can just go back if you're interested. So the first part is actually given history, patient history. So what's possibility that I really have diabetes? Okay, not true. So without considering the current observation. So that's the first part. Wait, that's the first one. Okay, imputation network. And for this one, we use a transformer because of the temporal relationship. And then propensity scores. This part is a bit complicated, so I have to explain it afterwards. Okay. This one we use RSCM and then tensor. I'll talk about this afterwards. Prediction networks. If we can really factorize these latent compute data, we then really got IBDs, okay? And use that to do predictions. Normally, okay, we get better if that's estimated properly. And for the propensity things, it is the key. If I recall, right? So we want to estimate propensity for every single zero. Very imposed problems, right? So let me recall. I have here the link up with what I talked about before. So these are data sets that we have for each patient, right? Clinical features, right? Basically, one slide of data. Okay, and then you can see many slides, right? Why we have the different length for different slide? Because different patient may have different length of stay in the hospital. Some longer, some shorter. If you stack all those slides together, you have this irregular tensor. Okay, for those of you working in this area, so PowerFact2 is a very effective method for that. And now we're estimating the propensity score, even though with that, a lot of parameters, a lot of things to estimate. Okay, so it's not good actually, because we believe that this propensity score should have some patterns. Otherwise, no chance that we can estimate that. Okay, so we just trade using low rank so that we can capture the regularities. We use a common set of data sets, okay, together with the weightings that can be estimated afterwards. Okay, so we also add LSTM here. For those of you working on the tensor, we add this here. So you have UN, right? So UI can estimate, can predict pretty well I+1. I+1 can predict pretty well I+2, just to do some regularizations. Okay? We believe that this propensity score will not change suddenly from time to 1 to 2 to 2 to 4. Okay, so all this are to make this propensity score estimation more likely to happen. Does it make sense? Okay. So with this, again, of course, we have for the training of the architectures, we also need some tricks. And you can refer back to it. I won't spend time to talk about this. Evaluation. So first of all, imputations. How to do these experiments? First of all, we use MIMIC-3 eICU, the dataset from ICU dataset. And we also develop, we also follow some other people as well, come up with a missingness model. Okay, and we use the model to remove some data. And for that model, we can control the bias and the missing rate. Missing rate is how often we cannot see your data, even though you have it. And then the bias is that how different are those zeros could be, the percentage of different zeros could be. We can control that. Okay. So increase the eta, okay, the bias will increase. And so you see that that's, of course, blue lights are methods, okay, which actually is better than the others with a pretty obvious margin. Okay. So the key message here is that if we can model the observation bias properly, that actually can help to deal with the missingness. I try not prediction error result also better. Okay. So I like this picture. It's more appealing. One patient, one slide, one patient, clinical features and time. Okay. And this is now another patient. We just pick some cases which look really good. So this is the observed data. Okay. And that's the ground truth. The red ones are those missing. Okay. If you use the observed one to do prediction, label of this one is 1, label this one is 0. And also, and the prediction, if you just use the observed, 0.05. And this one, 0.1. And with the pipeline, filling up those missing data, we can actually do a pretty good job in estimations. So, so that's our lessons learned. And I personally believe that maybe we can just spend more time to think about whether the observation bias that we use is that sufficient? Is that good enough? Is that really everything? And also we use the tensor to do the regularization. Is it again good enough in terms of the algorithms? So okay, so probably have to move on. So the first one is just unimodal. Okay, we just make use of the MIMIC-3 and then the eICU. Yeah, they record the data in the database. And for this one, because the professor did, so I have to talk about this. It's multi-modal. Yes, we have data from electronic health records. Yes, we sometimes, some cases, we also have X-ray images and other very different modalities, right? And fusing them is very important. Example, say pneumonia. If you have pneumonia, if you take a blood test, normally it will indicate some infection status, immune response. Right? But different parts of our bodies can trigger that. If infection can happen in different parts of our bodies, right? So the X-ray, if the X-ray image also indicate that, that is additional evidence that it's really having pneumonia. I am a computer scientist, right? That my wife is a medical technician, so I asked her. I grabbed this from the paper. Some papers say this. Okay, does it make sense? She's integrating data from different sources is very, very important. Okay, because they have to exclude cases. Okay, so that there are different evidence, so as to make a diagnosis. So fusion, I think, of multimodal different source of information, so to make a diagnosis is super important. Okay, so no doubt. But then sometimes we may not have that. Okay, we know, and clinician may request. Okay, that's good. Okay. But for computer scientists, machine learning people, we cannot just ask the patient to come back and then try again. It's impossible. So missing data is there. Common practice, some people will do it. Okay, okay, remove those with the missing data, and then we just focus on those that are missing. Okay. And lessons learned here, I'll show you afterwards. If you consider also those with missing, actually you gain something, because otherwise you follow away too many. So so missing modalities is the problem that we would like to do better. So that either you have this EHR here, and just in those from the structured from the database, together with X-ray images. Okay, X-ray is missing, and so we hope that the methods can work for both. Either you have both or you have one, still work. And interestingly, there are some inconsistency. If you use say data in structured data, the predictions and X-ray, they may disagree, they may conflict. Okay, so combine them. How? There are many different ways to combine them. There are many work. Okay, we have one way to deal with that. Okay, and to combine them, fusion. We also need to combine them adaptively, smartly, because sometimes it depends on the health conditions of the patient. Right? Okay. But these are something that we have to consider. With this understanding, we decide our I skip this because of interest of time. So this is what we decide. Okay, it is important to make a sexy name, so we call it Prof abuse. And I try to explain this. So from the left-hand side, we have two modalities, right? One is EHR time series, clinical features over time. And the second one is just X-ray images. Okay. If you forget about the middle part, okay, so the red parts, we can use some encoder. And here we use, because of the time series, we use transformer. And then for the chest X-ray, and here we use CNN, ResNet 50. Okay, just an encoder. Okay, lots of people using that. You just pick these two, and then we can learn representations, some feature vectors. We learn it. Okay, and combine it and do recognitions. Right? It's not good enough. Okay, why? Because as I mentioned, right, there are different information stored in different modalities. Okay? So what we believe that, okay, that actually, and also some are missing. So what we want to do here, we add another pair of encoder. And for EHR time series, we add one more transformer. And for X-ray, we add another CNN encoders. Okay. And what's the purpose of these two blue encoders? You see the subscript. You have very good eyes. I can see. We put a subscript shared. Okay. So from X-ray data and also the time series data, there are some information shared that you can extract from there. But each modality, they also have their own distinct informations, right? Otherwise, people don't have to make several observations. Right? So we want these two, the share part, to be as close as possible for two modalities. But why we want to do this is basically because some of this can be missing. Okay, suppose. Okay. If this one is missing, how to do the fusion? Okay. Then we say, okay, try to find some way to impute it. How? Okay. We do it this way. If we can learn these two encoder so that they share the information from both modality. Okay. If one is missing, this one is missing. And we have enough reasons to believe that this one, okay, actually is a pretty good imputed versions of this one. And that's the rationale. To do this, we try to make the distribution of these two as close as possible during the learning. Okay, we just define a divergence, make that happen. And then how about these two? We want them to be distinct from the shared information as much as possible. Okay, for those of you working in machine learning, okay, we can just add one more loss function. Right? Okay, basically, we use cosine similarity, okay, and then make the loss accordingly to make these two as distinct as possible, and make the middle two as close as possible, and then the whole things. Okay, so this is a way to deal with the imputations and the fusion together. We don't do imputation explicitly. We do it implicitly and through the learning, so that the other modality can have a pretty good representations of the other missing one. Okay. So there are some details. So if you're interested, we can talk about this afterwards. Okay. And that's the first part. Okay. And the second part, okay, after this, talking about different two modalities or more, which one to be considered more important. And I try to argue that sometimes depends on the patients, sometimes depends on the health conditions, right? Which is somehow captured by this representation, different representations being captured. Okay, we use that for those of you who know. Okay, we use some particular design of the attention mechanism. Okay, so as to make it disease aware. Okay. There are some specific designs on this one. You can make again. You can make reference to the paper. And so that's how this architectures were decided. So based on what we understand about the problems that we are facing. Experiment settings. Actually, we cannot do the experiments some years ago. Okay. In order to do this, we need this EHR time series, series of clinical features, X-ray image paired. Right. If you talk to hospital and give us this data, it will take, I don't know, in Hong Kong, it takes endless time, because that's not a concern, privacy, whatever. Okay. And for those of you, I really have to thank the teams, the MIT team working on the MIMIC board now. They released the MIMIC MIMIC-4 was released last year. MIMIC-CXR was released in 2019 from the same unit, same hospital, same hospital. That's why you can trace and can link up. Okay, so these are corresponding pair. If you don't have any pair, then we no point that we can do missing modalities. And then see for some details that we actually follow some previous paper for this concept. But I think this is interesting for you to know. Okay, and so we also make the training set like this. Okay. Really paired out of this 59 ICU stay with around 10K, which got paired. The remaining missing. Okay, for missing, I'm talking about the X-ray is missing. Okay, if we only get the pair, so basically the matched subset, we use it for evaluations. But the full data set basically include also those missing. Okay. If we make use of the full data set, the performance does not improve, which means that using missing data is not. But it can improve, which means that please do not just throw away the record of missing data. Actually, there are some useful information there. Okay. So, okay, we did experiments. So, train with the matched subset, with the pair. This one full data set with pair and missing. And of course, as usual, we compare with some existing methods. Okay. You see that there are some improvement. And even I train with the matched small subset and perhaps in the big one. Okay. So our method is still better than the others. And if you can train on the full, consider also the missing. So you can compare these two. This further improves the accuracy. Okay. So I think this is the main message I would like to share with you for this one. Okay. And yeah. One more thing is about inconsistency. Right? I mentioned that for different modalities, they may not give the same result. Right? So if I'm sorry for the small font for this line. Okay. The key message is for this line, I only use X-ray. For this line, okay, I only use time series. Okay, for single modalities, and you see that the accuracy is different because they give inconsistent results sometimes. Okay? And for say, I picked some good case for us, of course. Right? For the conduction of this order, okay? So Matthews, I think, is one of the method proposed last year recently. Okay? You see that they actually a drop by 40%, which indicates that if you fuse more than one modality together, but not in a proper way, actually that high. Some say yes, some say no. Okay, so what to do? And this is our work. Okay, so I think this can retain the original accuracy, and there are some others. You can find more details in our papers. And the last thing I really want to say is our recent 2 years early. Okay, I'm also interested to move to X-ray, and generative AI is so popular, and there's someone working on report generations. Okay, so our proposal somehow got funded. Okay, so start working on it. So and background again, multi-modality, but this time X-ray and text. Okay, so the life of radiologists, at least part of their life is like this. Look at different X-ray. Okay, of course they can make diagnosis, but normally they are asked to write a report. Very time consuming. That's what I learned from the radiologists. You can also check with some colleagues. Every day they have a lot of report, and that's why in many data sets, this one is absent because it takes time. Okay, but anyway, so that's their life. Okay? Every day they have to write a lot of report based on what they observe at X-ray. I also try to learn from some radiologists what their concern when they are looking at the X-ray, and then a little bit about the abnormalities that people will identify in X-ray images. And of course, the question is whether we can build some tools that can generate this report automatically, We're not going to replace the radiologists, okay? Don't be scared. But this is tool. They can have a draft and they can modify. Okay? I'll get back to this one afterwards. And to start with, so we work on this and then try some existing model. And then we compare the burst score. You know, for those of you from NLP, you know, checking the fluency, we use burst score. The burst score is not improved much. Okay? So very annoying. And then we look at the paper, report that we generate. There are something different. So the key idea is we're not just concerned about the fluency, how nicely this report is how fluent the English is. Accuracy is the most important thing. When I talk to some clinicians, they say, I don't like point form as long as they are correct. They don't need beautiful English. Okay. So that's why we also define our metrics that extract those clinical terms and see whether they are accurate enough. For the others, burst score, you know, we did not put too much attention on that. And then, so based on that, okay, we picked a particular approach that people are using. So again, X-ray, output text. Typically, people use encoder and decoder, right? So encoder, some representations in the middle. Decoder, encoder we use visual because we have image. Decoder we use text decoder because it's text, right? Reasonable. And for the in the middle, so the representations. So there are different tricks has been used before. And when we are working on this, some people use the knowledge graph. That is in the middle, they represent not only the abnormality, but also their relationship. Okay. We believe that if this happened, that probably the other abnormalities could probably high chance to happen, something like that. Okay. So that's the ideas. Okay, someone have done that. However, when they come up with this graph structure, they do it manually. And the fact that the graph that they have is talking about 20 nodes. Okay. 20 nodes is pretty small, but they actually using this 20 nodes graph, they can show improvement already. But the question is, can we, rather than manually creating this graph and then every single application will create a graph and pass it, can we automatically generate that? Okay. So that's the approach that that we use. Okay. We RADLEX, okay, RADLEX, RADLEX is one ontology developed by I think some radiologist associations. Okay. All these ontologies are standardized. They are developed by different associations. And we make use of that. And also corpus of the free text report. And we extract information like this. Okay. Of particular abnormalities, say fluid effusion, effusions, which is a quite common disorder for lung. And based on these fluid effusions, in this free text report, we extract different attributes, normally too big, too small, left lobe, right lobe, both lobe, things like that. Okay, so these attributes from these ontologies are normally go together with these pro-effusions, also for the others. Okay, and these are just set and subsets, right? And how about the edges? Okay, the edges will basically count the co-occurrence in the report. Okay, and then create the edges. Okay, form the structures. The nice thing is that, you know, we pick the co-occurrence statistics, right? And you can set threshold. Okay. Anything's more than 5, then from the graph. Anything more than 10 from the graph. Anything more than 20 from the graph. Okay. If you set a threshold higher, the graph will be smaller. Right? If you set threshold lower, the graph will be bigger. Okay. I think we are trying about 100 nodes versus what being tried to construct 20 nodes. Okay. You know, creating a graph with 100 nodes manually is not something very enjoyable, I believe. Okay. So that's what we have done. And also, I deliberately mentioned about attributes because in the radiology report, other than they say some anomaly, they also describe the details, the attributes. Okay? So I believe that if we cannot capture this information in whatever graph in between, how come we can generate a correct report, right? So that's why I think I try to talk to my students, of course, right? Okay, let's go for an attributed graph structure and learn the embeddings accordingly. Okay, so the design is a bit not so easy to make it work. Okay, so I won't go through the details because you can find in the papers. So basically, we produce an anomaly graph. For each graph, we have to attribute graph as well, and then we learn the embeddings. And visual encoder, that's that. Text encoder, we try transformer and also SDM, two level. I don't have time to talk about the gating. It turns out that, okay, we have to align the concept capture here and this text encoder. If we can align them better, the performance can improve with the gating methods, which we can find the details in the papers. Okay, we spent quite some time to make that work as well. Okay, so that's the point. So it's not just plugging in knowledge will help anyway, but to plug it in and we make sure that the knowledge is well aligned with what we're expecting. Thing won't just work as a black box. Okay, we really know something about a problem and get some of this model. So that's our own experience. I try not to bother with too much details. Okay, this is basically telling you that. So A type is what we proposed. Okay, together with the gating network. Actually, these are significance. Okay, significantly better than those without using the graph as the intermediate representations. Okay, and so we are pretty happy about that. So again, I'd like to show these case studies. This is the ground truth, right? Images. This is the ground truth report. If you don't use knowledge graph, just plug in transformer. This is what being produced. Okay, all are incorrect. When you see the color, the colors are the correct medical concept which is being generated in this report. Okay, and you see that processing is not really good, but anyway, it can capture most of the medical concept. Okay, that give the accuracy high. Okay. So that's the clinical accuracy that I'm talking about. So yeah, I quickly conclude my talk. Okay. So I share with you a few works that we have recently published. PatNet. If we can do something about the observations model for the missingness, we find this approach is promising. For doctor views, okay. So we find at least to propose some implicit way to do the interpretations at the latent size. At the latent size. Okay, you will probably learn the shared representations. Okay. And then I ask myself, can we impute? I'm talking about EHR time series in X-ray. Can we impute in the data space? Can we generate the X-ray report? We're working on that. Okay, we're working on that. Okay, so it seems possible. Okay, and someone don't like it because I don't know. We can have a lot of discussion, but I think as well we have to be open-minded to try whatever is possible. You know, the diffusion network is really powerful in generating images. So somehow it's possible. And also I'll talk about, you know, we use the low rank tensor, okay, to model capacity score. Can we explain that? Can we explain what's happening, what's driving the missingness, so that we can have some insight how to deal with that? Okay, so I didn't talk anything about interpretability, explainability, because I'm not working on that. But if you're working on that, okay, please help me, okay, to find a better way to handle that. Okay. So for align with our knowledge, we show that it can actually is pretty effective. You know, we just use embedding space to align them. Okay. It's pretty effective tools. But if we align them not properly, you also cannot see the benefit because there are some conflict between knowledge and the data. Okay, I can share more if we have time. I cannot end without talking about foundation models, right? So I did some fundamental work on foundation model, but have not integrated that into the healthcare settings. And there are many healthcare-related foundation models that we build, actually. Can we distill some of the knowledge from that? Okay. We do whatever tasks that we're doing efficiently. Okay. Our different modalities is also something that I think is good. Okay. But these are more focusing more on the algorithms. I want to conclude with this one. I like this one a lot. We are only solving a problem at a certain point of this whole picture. We have not yet understand the complex relationship of all these, and all these are in a clinician's mind. You know, look at different modalities and probably patients are suffering from this and that. Okay, so I always think that if we can look back on the real problem that clinicians is addressing, can get up ideas. So what new problems use and what new algorithm can be solved. Okay, again, remember multi-modals cannot be escaped. So with this, I think thanks for all your attentions. Okay, all this is collaboration with students. Okay, some of them graduate already, and then working as a REP in our departments. These 3 victims still here, and I'm still bothering them time to time. And so yeah, that's it. Okay, so welcome questions and comments.
Thank you, William. Considering time, I will open the floor to online audience first, because I think you can still reach to William. By the way, as I mentioned in the beginning, William is visiting us for 3 months, from January to mid-April. Therefore, for those online audience, right, if you find William's talk and work is interesting, you can still reach out to William, and yeah, if convenient, you can invite William to visit you. I believe he will be very happy to talk to you and exchange ideas. So can we open the floor to the online audience? Anyone online want to ask any question? Please unmute yourself and speak. If there are many, then raise your hand. Right, click the raise hand button over there. Anyone online want to ask question?
Hope that I'm not too over.
Yes, Samir, please unmute yourself. Unmute yourself, Samir.
Oh, sorry. Thank you very much for this this great talk. Really enjoyed it. Can you hear me? Yeah. So can you hear me?
Yes, no, yes, no, yes.
Oh, brilliant! Yeah, thank you very much for this great talk. So just I was really intrigued by when you mentioned how the numerical assessment of the model was not correlating or with what the expert reader or the radiologist were happy with. So what do you suggest is a good accuracy assessment of a large language model creating imaging reports?
Okay, so what I can say is just what we are doing. Okay, so what we learned from the clinician. Okay, so when they look at the report, okay, they care about accuracy. So that's why we extract the clinical terms and the related descriptions from whatever we generate by the AI, and then we use that to do the evaluations. And we also define evaluation metrics based on that. I think that will make more sense than just measuring the birth score that normally people use for tax qualities. And so whether we need to do some user studies, I don't know whether you're asking that studies or not. So we haven't started that part yet.
Yeah,
okay.
Let me a bit. In last June, we have a keynote from Morella talking about summarizing videos, right? So I think in her talk, it's online on YouTube, she also mentioned about these kind of things, like trying to identify a few facts, right? So known facts from the video or drama series to try to evaluate how accurate the summary is, right? So I see there's some relationship over there. Yeah, please continue, Samir.
Yeah, for example, pneumonia is actually is the fact is the ground truth, right? So it's really mentioned in the report that is considered to be good. Something like that.
Thank you so much.
Any other question from our audience? Please, yeah. Tina, please unmute yourself.
Yes, thank you. Thank you, William, for your great talk.
Thank you.
You can also turn on your camera if you don't mind. Yeah, so William can see you. Yeah.
Yeah. Hi, William. So I have a question regarding your radiology report generation. So I was wondering if the report generated by the model was have consistent format. For example, include the findings, impressions. As you know, in real world radiology, they don't usually generate very consistent or standardized reports. And if not, if the AI didn't generate very standard reports, do you suggest that using the reports template as an input to the model? What do you think?
Yes, thank you for the questions. Indeed, there are some work they make use of some template, okay, and fit into the representation in the middle, and then try to do the report generations. There are also some work they do retrieval. I think it's from the group from Stanford. Do the retrieving the relevant report, and then from this relevant report, they extract different sentences and compose them to form a final report. Okay. And so there are some, we also are working on some retrieval related methods on that. The rationale behind is that if you retrieve some report or sentences from the existing report, okay, that seems to be less a chance, okay, to come up with too subtle error or hallucinations that we don't want it to happen. Yeah, so I think that's the best way that I can answer. Okay, but it's indeed a good questions. And also, I'm also discussing with our students, if the reports are from different radiologists, okay, they have different style of writing that. Okay, so can we also take that into considerations in whether the trainings or the generations? Yeah, so that's yeah. Hope that it makes some sense to you.
Sorry, it's coming. Thank you. That's very insightful. And can I ask a second question about your prediction, the model on the tabular data? So I didn't see very much about you mentioned the different visits missingness, because you know normally in hospital every patient have multiple visits, and some patient they have all the patient have very different number of visits to the hospital or ICU admission. Do you treat the same scheme, using the same scheme, missing this imputation to those missing on temporal tampon and those missing at the same tampon? So what do you think, like, I mean to say, do you treat them different, or are you treating them the same, using the same imputation neural network?
Okay, yeah, thank you for the questions. If I understand correctly, right? So what I'm talking is within one visit, right? Within one patient journey. So we have clinical features over different dates, right? Which form one sequence. Okay, we basically just consider this to be a data point in our work. And what Jinyan's mentioned is that actually there are several visits, right? So William probably is a poor guy that have to go to the ICU several times, right? So several visits. And what happened in between, okay, that probably lasts for months. And then, so that is actually corresponding to a longer time, sometimes chronic disease. But ICU is critical care, it's acute disease. And for those between visits, we did some work before, which is related to the chronic disease, which the multiple visit, and we model the health condition change over a longer period of time. Okay. And the method that we use are very different. Originally, we thought they're the same. We just applied after that because we got, I think, over the chronic disease. Turns out, okay, all fell. Because for, say, within ICU, okay, we are talking about the critical care, the data is really dense. You have a lot of data. Say for chronic disease, say diabetes, you went to the medical doctors and then say something, and then I also have a high blood pressure, and then after some time you see the doctors again. Okay, and so speed is sparse. So so it turns out that we use some kind of a process model, okay, which I probably cannot just quickly explain that to you here. We use some kind of process model to model that. We hope that the dynamics can be captured by this process model. The quick answer is we cannot just directly apply for those methods which work within a particular patient journey.
Frame. Yeah.
In ICU sections to over a long period of time at different time scale. Our experience is that it just won't work immediately. We have to know what's happening at different scale of time.
Yeah, that makes sense to me. Thank you, William.
Thank you.
Thank you, Tina. Any other question from online audience? Please raise up your hand if you have, or just unmute and speak. Okay. If not, I will ask the audience in the room. Anyone have any question? Mohammed.
Hello, myself Mohammed. So my question is related to your missing modalities part and imputation part. So basically, you are currently doing like doing the missing modality imputations and like evaluating on like as a supervised like with the levels that 25 levels that is there like. So do you think like can your like imputation method can be using for pre-training, like for example, currently I'm working with like MIMIC for ECG, if you heard about it, and MIMIC-CXR. So when we like do the pairing, something like I'm working with the pairing one. So for example, the MIMIC ECG have 800,000 data, and CXR have 350,000 data. So when you pair it, just become only 52,000, something like that. So do you think that when we do the pairing, rather than doing the pairing, can it handle like this, that okay, there is pair like ECG CXR, then ECG no CXR, CXR no ECG, and both is there, so something like that, to like your imputation method for missing modality for the pre-training case? Because here you say that like you're using both shared and distinct modality features, which actually I'm also in my methodology I'm doing a little bit. So if we take both of them in the latent space, we can use that latent space for during our fine-tuning for any clinical like fine-tuning tasks. So do you think that if we this imputation method can be evaluated on like in pre-training part, then we can use large data set rather than just a pair data set for pre-training? So what do you think about it? Yeah.
Yes, good question. I probably will need some more time to think more carefully, so I cannot give you a very immediate answer. So that's supervised, that's true. Okay, and you're talking about unsupervised, right? Pre-training. So then the remaining point is how to define that loss functions so that works. Okay. So for that part, I think I probably need to think a bit more. Okay, definitely this is what we propose. Okay, in principle, that part we don't. For that part, we don't make use of the labels at all. Okay. So if we can define a loss function that can actually fit that one, that can explain the data, probably yes. But for this part, okay, we do make use of the label that this disease aware. We do make use of the labels because we want this attention to be able to capture the possible disease from these representations, right? So without the labels is very hard and to capture this disease awareness for the training. And for that part, the disease aware part, we do use the labels.
So what about like you are like preparing like if it is supervised pre-training rather than unsupervised? We have levels, and then we supervisedly pre-training, and then
Could be. For this part, we make it kind of pre-training, okay, and then define loss function so as to make this logic flow and works. And then probably the other part is the function. That probably.
so for the also another question is for the shared and distinct features. So did you had any experiments of like without distinct, without shared, like something like that?
Without shared, definitely yes, because we do the experiments on only one modalities. Okay, that one will fusing them definitely work better. I think if I remember correct, the transformer. I also have to go back. The transformer one, it's just using the time series, not using that. Okay, only one modalities. And then the other question is removing only using share. Okay? I'm not sure whether we touched that because we did all three. We actually concatenate all three to represent the health status of patients so that we can do this patients. Okay. If we take away to whether this is a good enough representations of the health status of the patients, we have a test.
Okay. Yeah. So what about the, I just have last questions, is that for the fusioning, is it like mainly compact? What's the fusioning like strategy, like methodology? Like how did you fuse the data? Like
How do I choose?
fuse the features, like fusion like methodology.
How did you combine the
Combine the
features?
features like
It's just a simple concatenation, right? So
Simple concatenation.
simple combination.
Because we concatenate that so that we consider it to be a good representation of the health state. And based on that, we have I didn't show the pictures, right? We didn't have a design on this attention. It's not simple attentions. We did have some design so that it can bring the disease awareness into considerations to see which modality should put more emphasis. Okay, there are some designs behind.
Yeah, thank you so much.
Okay.
any other question before we close? Cheung first, yeah.
Really, thank you for the wonderful talk. Can you go to page 26? I was kind of curious.
So mathematical department.
Yeah. Not 36. I think it was the when you talk about the transformer network. It was the Dr. Fields. Yes. I think it was this work.
Yeah.
So when you talk about, I was like curious about what exactly like the computational requirement for doing this is. Like how many GPU you need and for how long? Or like just rough number, because we are doing some project like this. And
I really have to ask my students.
right.
But as compared to large language model, okay, and the images, this one is much more manageable. Much more manageable.
Right.
I can say. Yeah.
Really, because the data is not that big, right? So it's
Yes.
because the paired one are only 10,000.
And then
Yeah.
I forgot the details of the size of the transformer. It's not that big.
Right. Because you have mentioned there is an image. I was wondering what's the size of the image. You were saying about 10,000.
Number of the images, right?
Resolution.
Yes.
Yeah,
Resolutions,
Yeah.
again, I have to double check.
Right. Thank you so much. Yeah, it's okay.
Thank you for the insightful talk.
Thank you.
I would like to ask a little bit about the Padlet, like the binary missing data imputation. To me, it seems like it is not only the missing data, missing value imputations, but also more on the data quality issue. Because like, for example, in the diabetes data collections, whenever we input 0, it may not actually mean 0. So there may be some data quality issue in there. Like, because I also worked on data imputation, but for my data set, when there is missing, I know this is missing. But like for your case or for your data set, maybe sometimes there are values there, but we just don't know that it is correct or not.
True. Yeah, thank you for mentioning this. As what I put at the very beginning, right? So that's our problem statement. It's a little bit different from yours. Okay, you have some real 0, right? Here we don't consider we have real zero. Yes. But if introduce the real zero, so then we will need to extend or modify our algorithm. So as that is the observation model, okay? So as to better represent the observation points. That's very true. Okay, but again, you say then the next issue is not about missing quality. Whether the zero is with zero,
Yeah,
right?
or one actually means one.
There are also many works in these days try to predict the confidence uncertainty of different values. Okay, which if I understand correctly, if you do it as well, okay, the performance, the accuracy can also improve. It can, yeah. So because this one work, and then I don't know whether it will be accepted or not.
And a little bit follow up, which I guess you already mentioned a little bit at the end. Like at the end, like the main aim or target of this model is to predict those missing values. We do have some assumption in between, like there may be some distribution or some reasons of why certain patients have some missing data.
Yes.
Do we actually like have some side products of like knowing the reason why certain value is missing as a explainable result?
That's exactly the question said at the very end.
Yeah.
So so far we didn't. If we really want to look into that, so we really need the three vectors that I mentioned, right?
Yes.
We need time from that to look at all those results with me, and then they have to understand what we are doing, and then hopefully some of the factors, right? Some of the factors that so these are the factors.
Yes.
Which the different combination of this explains all the density of the thing, right? But can these factors be interpreted?
Understand
Why?
human.
And understood by humans? So we have to, at this moment we have to surrender.
Okay.
And then so that's how we really need to work with the clinicians.
Another grant proposal.
Wow. It's not easy. It's definitely not interdisciplinary.
Yeah. Yeah.
But it's very interesting. But because if you understand this, then may provide you insights about the cause of the missing.
Or improving the protocol from data collection. Thank you very much.
Another question? Oh, yeah.
Hello, my name is Paul. Thank you very much for the presentation. So at some point you said that there is an inconsistency with prior knowledge, that different modalities sometimes give inconsistent information. I can imagine that it's like an issue in like a whole multi-modal field rather than only in just like medical. And so what I was curious about is whether you know of any research that tries to find what's the reason behind those inconsistencies. Do we understand this inconsistency? Where does it originate from? And stuff like that. Yeah.
Originally, I want to talk about one more works, but then I definitely know that I will overrun. So we also published a paper last year. So that this time is ontology together with EHR data structure one. So EHR, you know, we basically call current statistics, right? But you see models together. And then I also tried in, you know, use the representation learning, you know, learn the embeddings for different concepts and then integrate them. So we spent, if I remember correctly at that time, spent several months, cannot get performance improved. I'm very frustrated. Okay, so then because normally if you have knowledge, they can generalize better, but we get some. And then I asked the student, look at all those things in details and see what happens. And finally, I understand this for that particular scenario. The ontologies are created with some reasons, not for prediction. For example, I can give this example. That's ontology. As this particular versions of the ontologies, right? So this one is the category, injury and poisoning, which is put under the same category under IDD 9. Why? I don't know. Okay, because it's the convenience of classifying different disease and then take the statistic and then nations people will like know that, right? But somehow this makes sense, right? If there are some disorder which is all under this fractures of skull, it makes sense that probably these diseases should share some properties. Some are useful, some are not. Okay, so which part is useful, which part is not? So what we did is we adapt this ontology. If this category have data really support this, okay, putting them together, use it. If there's some tangent in between, based on some measure, we split it. Okay, and so that's the key idea of that paper. It turns out to be just this idea, and then we adaptively split all those categories. Turns out that we can further improve the accuracy. Yes, the data space organized much better because we have ontologies, but the accuracy gets stopped. Not until we do that. And that is back to quite some years ago. And recently we incorporate also this SNOMA again. And we also noticed that because they are created for different reasons again, but there are some inconsistency. It's not about the knowledge. If you just use them to the representations, okay, so they will pull things apart instead of supporting each other for some part of it. Okay. So our way is to make it more adaptive. That is, we allow if there are two concepts are related, so the embedding should be close, but we allow some flexibility. We again using attention mechanism to learn that flexibilities. Okay. So that for some concepts they're related distantly longer in latent space. For some still related but can be shorter. The same relationships. Okay. So to summarize, so when we integrate data with ontologies, when we integrate data ontology with ontologies using representation learning, yes, it's quite useful, quite easy, embedding stay put them together. Okay, but you do it not properly, the inconsistent information, inconsistent because of the way that they are produced, created, will limit you to get higher accuracy. So that's what we identify. Hope that answers your questions.
Any other question from online audience and people in the room? Sina, please.
Thank you for your interesting presentation. So I have two questions regarding the Dr. Few's method. So the first thing is that how balanced is your data? Because I think if you're talking about the missing modality, and for example, for the minority class, I mean, most part of the missingness are relevant to the minority class. Do you think that still the shared common space between those modality can be helpful?
Yeah.
It seems to be like a tendency of your model to the majority class, not the minority class. Is something like it maybe bias?
Yeah, that's very true. Is it data is quite imbalanced. Okay? We haven't put a lot of attention at this, so that's why we use AUC to do the evaluations. That's kind of taken a bit more into considerations, just for the evaluations. But whether we should do something about this imbalance situations in the trainings, we haven't done that in our work. But that's a very good question.
Can it weight, for example, each sample different way? I mean, for example, I don't know, the higher weights to minority classes and maybe lower weights to majority classes or something like that?
Could be, but we didn't do that.
Okay, another question is about the setup that you described for that method. It's like it's like 26 of the setup. The experimental setup. Yeah, about the number of features. I think, is it like a selected features, the selecting features, or it's just like the whole feature?
From one of the previous work, so that we can compare. It's from Matthews.
You mean we had the larger features, but you selected 7 features?
Yes, so that we can compare the performance.
How big was the features and the feature space? The original one?
Oh, of course, it's much higher. Yeah, because clinical features basically talking about different records that we have in the EHR, maybe 3 or 4. Okay. So the number of features are a lot.
Details selected manually?
This one, right?
Yeah.
So we the reasons for selecting this is there's only one, because we want to compare with Matthews, and then they use that. So that's how we use that.
Okay.
Yeah. Whether there's other way of selecting the features, we do a better job. Yes, I think so.
Okay. Probably we can close with one last question from me. Maybe when you have the inconsistency between modality, right? For example, modality A predict one number and modality B predict another number, right? So, have you considered the kind of confidence or uncertainty? Because if one model is very confident and the other modality is very not so confident, right? So maybe you will take the confident one, right? So have you considered this kind of uncertainty, or any other work have taken care of that?
Yeah, we haven't. Yeah, also very good questions. As I mentioned, right? If there are some other works, okay, if you predict also the uncertainty together with the prediction the labels, the performance will improve.
Yeah, it should.
But we haven't done that.
All right, let's thank William for a very exciting talk, and also I believe this will be a very unique interest from you for the missingness screen. Thank you, William. Yeah, thank you. So yeah, by the way, William is here, right? So until April. So if any of you want to and talk to William, you can email him, william@htbu.edu.hk, we will share the slides, I believe, right? So the video is also recorded, which we will upload to the CMI YouTube channel. So please subscribe, and we will let you know when it's up. All right, thank you, thank everybody online for attending this talk and all your questions, Samir and Gina. Thank you.